Okay, I had to go off and run a couple of chores, and I am back to try to finish up walking through the Cavendish experiment with you guys. And then I'll post some stuff that should help you to start working through an analysis, and I'll figure out how to do a time lapse video or something like that of the actual results as the instrument generates data. So let's talk about the rest of the experiment. And I'm going to have to move the camera around a bunch to do this, and it's going to be obnoxious and make you feel queasy and seasick. So I'm sorry about that. Okay, so you can see there the two optics that form the telescope. I can't actually remember now. I think I might have built a Keplerian. I might have built a Galilean telescope. I just can't remember. I was just picking optics that seemed to be suited to the purpose based on what was already in the drawer, of course. All right, from the telescope, we go downstream. Forget this. It's not actually in the beam path. It's just behind it. This is the instrument that was sent with the kind of kit of the Cavendish experiment. I think this was built by Leibold, which I only really knew as a vacuum manufacturer. They build like turbo pumps and that kind of thing. Anyway, they sent this instrument that has two infrared LEDs in there and then a line sensor. And I think you were supposed to do something like put this on the rail so that there's an optical rail here. Place this instrument on the rail, and then those two LEDs inside the slot, I think those are infrared, would emit light, and it would hit the curved mirror in the Cavendish pendulum thing itself. So there's a curved mirror in here. It would be, gosh, I guess it would be collimated if you place this the focal length of the mirror away from the pendulum on the rail. It'd be collimated, and then the collimated spots would be imaged onto the line sensor. And I think there's some mumbo jumbo where it figures out the position based on how the two spots move. There may be some processing you have to do to really back out the measurement. So I'm actually kind of curious to see if somebody can get that up and running. We have the software that came with this instrument back in 4000 BC when human writing was first invented in Uruk, Iraq, and maybe somebody wants to get that up and running. It's kind of it feels like a bit of a Rube Goldberg contraption. What we're doing is described in the materials that came with this instrument as well. We're just going to shine a laser beam onto the mirror here. Now, if this were just a flat mirror, we wouldn't have any of the problems that we've sort of talked about already. The mirror would rock back and forth, and then we'd see the spot reflected off that mirror down to a distant point. We'd see it move. Right now, you can actually see the spot on the far wall. So I'll rotate this this camera around again. I'll rotate the laptop, and you can see where the spot is on the far wall. You can see over there, there's a piece of paper taped to the wall as a target, and I've got some marks indicating where it's been moving. So the spot's moving even though I'm not doing anything with the test masses. Now, you could say like, oh, well, you're walking around the lab. You have a mass. Let's approximate you as a 100-kilogram spherical mass. Maybe you are pulling on the two masses inside the pendulum apparatus, and you're differentially pulling on them and causing the Cavendish pendulum to oscillate. I don't think that's it. I'm pretty sure instead what's happening is I am bumping the table, putting stuff on it, moving things around, leaning on it, and that is causing the Cavendish pendulum to oscillate a little bit. So I've marked out a typical sort of sweep there as the thing bumbled around. My hope is that it's just due to table bumping and it's not due to some other sort of instability in the system. What are the two most likely things that are wobbling around? Well, one, where is it? The laser. This is really jankily mounted, right? It's on these tall posts. So those posts are free to wobble back and forth. If they were shorter, there would be less of an issue, but the height there is determined by the height of the Cavendish pendulum apparatus. So we're going to stick with that for the time being. You could do something fussy, like put the telescope, put the laser, the telescope, and some of the optics down really close to the table, put them on stiffer mounts, and then use a periscope to bring the beam height up to the level of the Cavendish pendulum. We'll do that if we have to, but it's not my first thing that I'll try. My first thing is I'll just mount this a little bit more substantially. That's a really janky way of doing it. The individual optical components, like these mirrors, these are also, great big cantilevered things. So I could do a couple things to improve the stability of that. The telescope is a really ugly looking cantilever type thing, right? It's attached at a base here to the table, goes up to this thing, which is just free to rock back and forth in the cool summer breeze, right? So that's horrifying from a stability point of view. And then we have the pendulum apparatus itself. So let's take a look at that. Okay, I just wanted to put a weight on the side of the laptop so it wouldn't rattle around a lot. Okay, so the Cavendish pendulum is inside this housing that's designed to minimize the amount of air currents that are flowing over it. There is a wire attached at a single point up here. The wire depends down from that attachment point to the center of the apparatus. Sorry, I'm moving stuff around to try to get a better shot of it and bumping the table a ton as I do so, incidentally. Okay, at the bottom of the wire is the pendulum weight itself. So there are these two masses, one here, and they're of some dense metal, almost certainly lead. They're connected by a thin bar. And then in the middle, there is a mirror, that concave mirror I've talked about 1,000 times. What else do I need to mention about it specifically? There are these two knobs here and on the other side, and those are meant to lock the pendulum in place. They can be adjusted, so they'll bring up a little sort of metal, not quite a knife edge, but a metal edge that will hold the pendulum in place so you can transport it without bumping things around too much. The apparatus mounts on a rail, which we don't really have any use for. I could have just mounted this in a regular optical post holder, but this post is not the standard 1/2-inch diameter that all the Thorlabs and Newport and other parts I've been using are. I think it's an older part built by maybe Oriel, and it's probably like 5/8 of an inch or something like that, or 3/8 of an inch. I can't remember if it's too big or too small, but it doesn't fit tidily into the ubiquitous 1/2-inch post and mount hardware that we all use now. Could we make it fit in something? Yeah, absolutely. We can get away from where this is mounted, but that clamp bolts onto this rail, which we really don't need because we only have one component on the rail, so it's superfluous, but it was an easy way to get this thing on the table. I just dogged the rail down onto the table with a couple of clamps, and again, a pretty janky style. Normally I would say that's fine, except on the other side, let's see if I can show you guys this easily. If you heard me just put that thing down sharply on the table, that's another thing that's going to cause the pendulum to wiggle. This is a really terrible way to try to take a picture of something. You see all that paper wedged under there? That's me shimming the thing. So why did I have to do that? I had to shim the Cavendish apparatus because when we bolted it to that rail, which was mounted rigidly to the table, it turned out that the table's not leveled. And that's because it's not resting on its pneumatic piston legs. It's resting on, I would like to tell you it's just resting on the legs, which are themselves just deflated, but it's actually resting on some of the legs and some wood stock, just 2x4 material that we used to shim the table in place while we were bringing the two tables together to mate them with the mating plate. There's this tedious process of bolting the things together very carefully so that you make sure that the two surfaces are both perfectly planar, and more importantly, to make sure that the mounting plates are actually joined properly, so you have a good plate-to-plate contact, and you don't have one cupping and resting unevenly on one surface. If you have cupping, then you only really have contact on those plates just around the edges. You want to make sure you have two very flat surfaces that are then bolted together under a lot of tension, and that'll give you the best joint between those tables possible. So, like I said, I got to go buy $8 worth of polyurethane tubing and inflate these table legs. And then when we do that, that pneumatic cushion will helpfully decouple our table surface from vibrations in the floor. And vibrations in the floor are coupled into vibrations in the ground around us, and vibrations in the ground around us are coupled into the vibrations of trucks on the bypass. And you can absolutely detect this kind of noise with a precise interferometric laser measurement. We're not doing that kind of precision, right? We're not too worried about you and your Corolla driving along the bypass. But in most buildings, you'll have acoustic noise transmitted through the floor. Is it because somebody's using an elevator that is also rigidly mounted into the building structure? Yeah, maybe. It's very often due to HVAC stuff. When I was at the Franck Institute in Chicago, the building is built in two wings, and all of the HVAC system is in a machine room in one side of the building, which is on a separate concrete foundation from the other wing of the building. And that way, all of the acoustic power, all the noise power generated by the machinery is really limited just to one wing of the building. Whereas if you're in the other wing, you have a more quiescent foundation surface to build on and then to do your experiments on. So we have the pendulum itself. Let's go back to that for a second. There is a single point harness for this wire that depends down here to the pendulum, consisting of the two masses joined by a thin bar. And then we have the carrier for the weights. This thing spins. What I'm going to do is put a large mass here and in the other carrier. And then I can move those masses close to one of the masses on the pendulum or flip it. So that will cause this pendulum to torque. And by measuring the deflection of the beam on the wall, I should be able to figure out how strong the force of gravity is between the mass I put here and the pendulum, right? I can get its moment of inertia. I can figure out almost everything about this thing. The one figure of merit that's really helpful to have, though, to make your calculation simpler, is to know the spring constant for this wire, right? It's just a Hooke's law oscillator. The thing will rock back and forth. And it does so with a restoring force. If I perturb it out of its equilibrium, there will be a restoring torque that brings it back to its equilibrium. It will overshoot. It will go in the opposite direction. The restoring force will bring it back to its equilibrium. It will overshoot. So it's going to rock back and forth like this, right? And it's a damned Hooke's law oscillator. So in my 211 class, we studied that problem to death. You guys should all be pretty comfortable with the DFQ for that. All right, so what else do we have to think about? Well, the simplest calculation to figure out how the Cavendish pendulum works is to say, let's pretend that the torques involved are this mass pulling on that mass and this mass and the other carrier that's behind us. Let me just make sure you know what's on the other side of this thing. You see how there's the other carrier? So we're going to say, oh, the torques on this pendulum are this mass pulling on that mass and this mass pulling on this mass, right? And that's not all there is. First of all, we're going to neglect the weight of the thin beam that holds them together. That's not really true, but we can figure out how big of an error that introduces. Maybe more substantially, maybe not. This first mass will also pull on that mass. And this mass will also pull on this mass, right? So it's not just the closest masses that will pull on each other. You'll also have cross torque from that other term, right? So we can do some geometry and figure out what the expected magnitude of that effect is. What else? Well, my mass, like I said, if I wander up to this thing, I'm going to be pulling on it. What's the distance from me to that thing? Well, don't sit too closely. I can't remember any of the other corrections we have to think about at the moment. That might be pretty good for a starting point. I mean, we should probably do a bunch of trials at different temperatures to figure out how the spring constant for that wire changes. This thing was fabricated 20 years ago. Maybe we should be thinking, well, has there been relaxation of strain that was sort of cooked into the wire when it was what's the name of that process for drawing a wire? When a metal is very easily stretched into like a filament, there's a word for that. But again, I'm just too tired all the time these days to remember things like that. Anyway, when the wire is fabricated, there's probably a lot of strain sort of cooked into it. There will be then fast relaxation after it's fabricated and slow relaxation processes. Well, it's 20 years later. Maybe there's been some slow relaxation processes, and maybe this wire has a different spring coefficient, spring constant than it did when it was fabricated. I don't know. All right, so let's go and take a quick look at the spot and see how it's moving. My goodness, a spot on the wall. So I drew some marks just to show where it was tracking back and forth across the, sorry, I got transfixed by looking at it wobble. See how it's moving as it goes back and forth across the piece of paper. You can see it's got some up and down motion to its wobble now. That is absolute proof that it was bumped when I was over there, because it was not doing that before. It was just tracking left to right. So that's an argument for me being able to bump it. And maybe that was the cause of the drift in the first place. But then again, I'm looking at it and thinking, well, that's got a very characteristic sort of motion. That's not the same as the slow left-right sweep I was seeing before. Sorry, I just got distracted and realized I wasn't probably pointing the camera where it ought to go. So maybe this little wobble it's registering now is different from the slow translation I was seeing. We'll have to think about that. Anyway, there's a distance between the 2 points. So let's take a look at that. You can see there, let me get my finger lined up with it. There we are. There's the Cavendish apparatus. There's the spot on the wall. So the distance between the two is the run out between the mirror and the point where I can measure the translation of the spot in order to figure out how far the thing has rotated, right? That's just some basic trick. Okay, so I'm not going to actually do a scientific measurement tonight because it's 8:30 at night and I want to go home and have dinner. But let's take a look at what happens when we add the test masses. The real thing that's going to happen is we're going to perturb the heck out of that system, and it's going to wobble like mad. So that might be all we're observing. It might be the case that I have to finish floating the table and remove that shim material from underneath the rail, bolt it down properly, make sure the whole thing's leveled, which we'll do by adjusting the height of the pneumatic pistons, so we won't have to worry about shim stock anymore. Bolt the thing down, and then maybe we can do the experiment. But if I remember correctly, one of the things you have to keep in mind when you're doing this is each time you poke at it in some way, you need to give the experiment like 45 minutes to calm down. It's a little bit like me in that way. So we'll go put some masses on there and wiggle them around just for the heck of it. It's like a little shot put. It's like the one you get when you're in kindergarten. It's your first shot put. So we've got 2 of these. I can't remember what they weigh. Maybe like 5 kilograms, something like that. I masked them. We've got that information. I feel like I should just be able to judge it, but somehow that skill has failed me right now. So I'm going to place them in the carriers and see what happens when I do that. I do think that I will basically just be perturbing the system in such a way that we'll see a lot of wobble, but maybe we'll also see some good tracking from the gravitational force pulling this thing. Look at it go, right? So that is the mirror rattling around up and down due to the bump it got when I put the weights on the carrier. Now, I'd like to tell myself that that motion off to the right here is due to the gravitational pull on the pendulum, but maybe that's also just it being bumped. I can't say. I'd have to actually think about it and tell you what I think the expected magnitude of displacement is. So you can do tricks like, you can do a couple of different measurements with this, but one thing you can do is to place the masses in one position and wait for the pendulum to come to its new equilibrium position. It's going to oscillate, right? But that oscillation will damp. So you find that new equilibrium position with the masses there, and then you just reverse the carrier position. You rotate that carrier to the other side so that it torques the pendulum in the opposite direction, and it will move to its new equilibrium position, overshoot, correct, wobble, and you'll find it coming to its new equilibrium. So we could do a measurement like that. We could do, I guess, what we'd call a static measurement, where we say, oh, we added the masses and it moved off here and came to a new equilibrium. Then we moved the masses again and it came to a new equilibrium. Having done that, maybe we could figure out what the gravitational mass, what the gravitational force is between those masses. The other thing you could do is to look at an oscillatory signal like this and work something out. I think looking at the period, I have to work through this again. I thought about this before we started the semester, but it's been a minute, as the cool kids said, 15 years ago. Anyway, I'm gonna watch this thing for a little bit and talk about how far it moves, and then maybe we can start thinking about what that implies. But this is probably a good point to pause the video anyway. Okay, here's an update. I don't know, 5 minutes later, something like that. So when we started out, the laser spot was, let's see if I can find it, bopping along in that row of black circles, right? So that was roughly centered, presumably, on its original equilibrium position. Then we added the forcing masses to the Cavendish experiment. You can see our beautiful chameleon laser in the background. That's our TISAF system. There are a bunch of optical experiments that go on this table for our research purposes, but they've all been temporarily stored because we were moving stuff around from one lab space to another. Anyway, we added the forcing masses, and the spot immediately started zipping. So it moved from there all the way over to there. You can see there is a bit of tape with a mark and something that looks like a question mark. That's because I was actually moving the helium transfer tube out of the way when the spot rapidly reversed direction. And we know that's wrong, right? That's not how a Hooke's law force works. Hooke's law says that as you reach the extrema, the positions furthest from equilibrium, the velocity should drop to zero, and then there should be this moment where the object oscillating according to Hooke's law is momentarily at rest at its extremum. So that's not what happened. Instead, the spot zipped off to that side, and then it rapidly moved in the opposite direction. So that makes me think that it banged against the case maybe of the Cavendish experiment. I'm not sure. Anyway, that was the site of the first extremum. Then it rapidly zipped in the other direction over to here. You can see it's pretty dim. I need to get better light back here, I guess. You can see a spot. Again, it's approximate because the thing flipped direction very suddenly and abruptly, still with relatively high velocity. And I just wrote a 2 there, indicating that it was the turning point. So that was the other side, I think, of the apparatus. Then we swung back to pretty much our first position again, right? So is there damping? Sure doesn't, you can't see it because the transfer tube's in the way. There's another spot with 3 marked there. We had another rapid reversal though, right? So when the spot was there, it flipped again. It was going this direction, hit the extremum, started going back in that direction. So I think that that is the pendulum knocking into the case wall or something like that. That would tell us that the fact that it reached the same extremum is not indicative of it being a very high Q oscillator. Although I think it is, it's indicative of the system having another thing bumping off the pendulum or some other effect that we haven't considered. Anyway, that's the extremum that it hit. Then, let me see if I can remember this right. Oh, yeah. So we zipped away from that marker where I wrote a 3 over to, I'm blocking our beam, over to this marker where I wrote a 4. And that was the extremum it reached at this point. But now it was doing what we expect a Hooke's law oscillator to do. It was moving very slowly when it reaches equilibrium in reverse direction. So we could more accurately mark the side of that equilibrium. Not equilibrium, extremum, excuse me. The oscillator moved slowly as it approached this extremum, instantaneously stopped, and then reverse direction. And it looked like a Hooke's law force. You can see it's reached another extremum, and it's reversing direction again. And it hasn't gone as far as it did the first time because there's damping in the system. Let's see if we can write a little marker for that. Okay, I marked that extremum with a 6 because that wasn't the next thing. We had reached this extremum. Let me see if I can get it on camera. Marked 4, and then moved back in the original direction to this point. And this is actually not in the same location as the first 2 extrema over on this side. And if I recall correctly, when the spot reversed direction here, it did so according to what I'd expect from a Hooke's law oscillator. It slowed down, came instantaneously to a stop in reverse direction. So I think that's a real oscillation now that we're seeing from 0.5 onwards. Okay, and then from 5, we got to 6, that one we just observed, and now we're moving back in that direction again. So what can we say about this? Well, I think we're seeing a real shift due to the addition of the gravitational forcing masses. I don't know why I'm pointing this at a random direction. I guess I wanted people to see the lock-in amplifier. Okay, what can I say? I think we're seeing a real shift in equilibrium value due to the addition of the forcing masses on the Cavendish pendulum. I think that's what's driving this effect. There's a chance I'm wrong. What could also be causing this to occur? Well, maybe it's possible that shimming that thing has completely upset the way that the apparatus rests, and then when I loaded it, it did this. But I wouldn't expect it to do such a nice job of keeping the spot in a level plane if that were the case. So I'm going to suspect that that's not actually the real source of what's happening. I think it's the gravitational forcing masses that are driving this. But that said, I'm kind of surprised at the magnitude of the excursion, right? If this is supposed to be a tricky experiment to run, I would have thought I'd be seeing the spot move little tiny amounts, not large amounts. Anyway, let's see if we can figure out what the new equilibrium position is. And we're not going to do the more complicated experiment tonight because I haven't been timing any of the spots I've been putting down. And also, we shouldn't just be trying to catch the extrema of the fringe, right? If you want to observe some sort of oscillatory pattern, don't just try to get the peaks, because at a peak, the derivative goes to 0. So as I move back and forth across that peak, there's a change in time as my spot moves towards its extremum. There's a change in time going on this entire time. Where's the extremum? Is it here? Have I reached it yet? I can't tell. Have I already gone past it and I'm going backwards? I don't know yet, because this motion at that extremum is so slow and the object moves such a small distance in that neighborhood that it's hard to actually say exactly where that extremum occurs. Is that a big problem for what we're doing at the moment? No, but if I have a shape like this and I want to know where that peak is, the best way to find it is not to just try to find that maximum value, because the derivative goes to 0 there. So any small error I have in my location of my peak doesn't result in a big drop in amplitude. And so I'm not likely to pick up on the fact that I'm not actually finding my extremum. To find that, the center, to find that extremum location, what I want to do is trace out the curve, get a couple points on either side, and then fit it, right? So that's how I should be taking data if I want to observe this oscillatory signal. Don't just get the peaks, get the whole wobble, and then see what we can do. I kind of want to revisit something because I'm teaching it in 211 this year. When I talk about anything that obeys second order differential equation, I think about Q factors. And I take off my glasses so I don't look as hideous to myself in the computer. It's nice to be a little bit astigmatic when you're starting to worry about your appearance. Okay, if I have an oscillator, there's a Q factor, which is the amount of what? The amount of energy lost per cycle divided by the average energy during that cycle. I think, I can't remember now. There are actually, I think, two most common ways to define it. They have the same fundamental meaning. Who cares? The way that I think about it is, this is a really useful way for understanding an oscillator. If I have a high Q factor, then that means that the system can only oscillate at a very small range of frequencies. But if I set oscillating at one of those frequencies, the damping is very low, and it will oscillate for a very long time at that frequency. So it's a tuned system. The system wants to oscillate at just one resonance, and it will barely oscillate. If you try to drive it with a periodic forcing function, it will barely oscillate at other frequencies at all. But if you have the other extremum where you have a lot of dampening, the system can oscillate at a broad range of frequencies, but it will tend to damp out very quickly. We all have this bias where we hear, oh, the thing will damp out quickly. And we think that's the bad oscillator. The one that has a high Q factor, a very highly peaked Q factor, is the good oscillator. But good and bad are very subjective, because having a system that can oscillate at a broad range of values might be really useful to you, right? Okay, that's tangential to what we're doing at the moment. I'm not going to look at something that's supposedly a Hooke's law behavior, where the object's zipping along and then zips right back. I'm not going to look at that and say I can understand this using a Hooke's law force. I think that the spot was zipping along because the pendulum was rotating under the influence of the gravitational forcing masses, and then the pendulum hit the wall, or maybe one of those supports that's designed to lock the pendulum in place for moving the system, or something else happened that I haven't quite figured out. But I don't trust the behavior at that point. Instead, what I'm going to do is say, forget all that, and let's just look at the new equilibrium position, and then we'll rotate these test masses. We'll rotate these forcing masses and see what happens. All right, so let's go take another 10-minute break, and I'm going to go watch some more Great British Bake Off. Okay, so I waited for a long time, and the thing pendulumed back and forth, and I thought we were going to get an interesting result, but it looks like it's damped out to a final position right in the middle of where it had been bopping along before any of this started. If you remember, there was a range of circles I'd kind of been sketching, saying like, oh, it seems like the equilibrium position is somewhere in there, but I bumped the table and the whole thing's rattling around, so it's somewhere in that range. And then it zipped over all the way to there, all the way there, and then seemed to spend a lot of time going back and forth in this region. But it looks like the spot is back there. So that's like dead on in the same vicinity as where it was originally. So we're either doing something wrong, or the deflection is actually tiny, and we need to narrow down our idea of what the actual equilibrium position should be. The problem is I'm still bopping around in the lab, bumping the table and doing stuff. So this might be a flawed effort at getting a rough, fast estimate of the behavior of the system. I'm going to mark that location and then flip the position of the forcing masses and see if it gets the exact same like wild oscillation to start with. In which case, I'm pretty sure that is just us bumping the system, right? And then it has to damp out that perturbation. So let's find out. Okay, so I have more frustrating news. While I was marking my spot, saying, look, here's where the equilibrium is with the forcing masses in position 1, it seems like the spot moved. Is that because I was bumping the table, putting my laptop down? Yeah, probably. Let's just see what happens, though, when we switch the position of the masses. All right, so this is position 1. We rotate the masses to position 2 and see what happens. All right, let's wander over to the other side of the lab and look at that spot. It's moving, and it's definitely got some wiggle that it picked up. I think that this is probably going to be a frustrating way to spend the rest of the night, and it is 10:30. So I'm going to shut down for the time being, and then hopefully tomorrow, you can just see my mouth now. That's weird. Hopefully tomorrow I will be able to get this up and running and actually collect some data, and I'll stop coming over here and pounding on the table and causing this thing to rattle. It's definitely moving off in one direction continuously, and it's doing it like this. So I think that stutter step, that epicycle motion, is vibrations of the apparatus. And then I would like to think that the slow movement, which is much more sedate than that first thing we saw when we put those masses on there in the first place. I'd like to think that that slow movement is actually real, but I'm probably being naively optimistic again. So I am going to putter around for a few more minutes, see if this thing does sensible stuff, and then wrap up for the night. And then tomorrow I'll generate some real data for you. One last thing I should say about it. I mean, I'm probably going to do this 5 times. Each time I'm going to say, oh, one last thing. I think actually me getting up, moving around, I kind of do think that's responsible for driving that first shift off of my mark. So that's probably a good sign that we need to set this thing up and then not try to work on a laptop that is 5 inches away from the apparatus. And I knew that. I'm just being an idiot and not doing things sensibly. Anyway, if you can see way over there on the wall, our spot is, I think, still drifting further and further away from where the equilibrium was found with the masses in position 1. So we've moved it to position 2, and I'll see what happens. All right, let's see. Okay, guys, I think I'm giving up and going home. I've said that since like 8:30, but I think it's true now. Forgot to plug the microphone back in. All right, so I was just saying, I've been saying I was going to go home since like 8:25, and it's now 11:34. The laser spot is wiggling around. That spot over at the far side, right there at the edge of the screen now, is the one from when we had the forcing masses in the first position. And then these adjacent spots are where the laser spot is bopping around now. It seemed to hang out in this region. For quite a while, and then started to sort of wiggle back towards that same equilibrium position. So I think I really have to take to heart the idea that you need to wait like a substantial amount of time between each change for the system to equilibrate. And that's fine, but it's 11:30. So that's quitting time and then some. All right, so I'm going to wrap this up and post this video. Hopefully I'll get some data out for you guys tomorrow. I bought some Raspberry Pi webcam modules, and I was hoping I'd get these connected and set up so we could just basically say, all right, you know what? I'm not taking this data, you are. And maybe we could capture a time-lapse video or something with it. We will see how far I get with that, because I absolutely hate doing that kind of chore. But it's got to get done, right? So I'll see about generating some data for you tomorrow with this same janky way I'm doing it now. An awful lot of things have been described as janky today, but that's appropriate. I will see about getting you some data the same way I'm doing it now. And while that is running, I will see about getting a webcam set up and ticking along. So we'll see if we can make that work. All right. Feels like I should say something important at the end of a long day of recording stuff for you guys. But I hope you're all doing well, and I hope that this has been as interesting as I found it. Watching over somebody else's shoulder while he or she turns knobs and presses buttons is a little bit boring. So I understand if it wasn't the most enthralling few videos. But maybe, just maybe, it kind of scratched an itch for you guys to be in a lab and doing something as opposed to being stuck at home or stuck at home, right? That's where I'm spending all the rest of my time. All right. Good luck, guys. Stay healthy. Wash your hands. I miss meeting with you on Tuesday, Wednesday, and Thursdays. It's one of the best parts of my week. Hope you guys are doing well. Bye-bye.